All right. Remembering now with exponential decay, so remembering if we were to have a look at what exponential decay would look like, it would look like something that's coming down and approaching zero, but remember, never reaching it. So it gets close to zero, but never reaches it. And radioactive decay, so your carbon dating, etc. We know that it decays at a certain rate, so that's how we can estimate the age of things, because we know that the radioactivity left in some of the bits and pieces must follow this law. The cooling of a hot liquid would follow this as well. Initially it will cool down faster, but as it starts to get closer to room temperature, it slows and slows and slows how quickly it cools. Depreciation, so declining balance depreciation, also follows this law as well, that something will start off at some initial value and decrease over time, but never actually reach zero, but is effectively worthless after a certain amount of time. So running through a quick example on that. So example 7, a small rubber ball is dropped from the balcony, h meters above the ground. After each bounce, its height can be modelled using the formula. The height is 12 times 0.6 to the power of b, where b is the number of bounces. So a couple of things that's going to give away that this is exponential decay. So if I was just to rewrite this, h equals 12 outside of 0.6 to the power of b, that here we've got a decimal, so which means that value of a is larger than 0. Hang on, let me rewrite that better for you. A, it's bigger than 0, but it's less than 1. So because it's in between 0 and 1, it's that decimal is going to be a declining, a decaying model, and our power is positive there as well. So that because we've got that decimal with a positive power, it's declining. The other interesting thing to notice is that we've got this 12 out the front. We're doing 12 multiplied by something. So we know that the initial value, the very beginning, the y-intercept, is going to be 12. And just bouncing ahead through the questions, to question C, what is the height from which the ball is first dropped? Well, that's 12 centimeters. It's in meters. So it's not 12 centimeters, it's in meters. So the ball is initially dropped from 12 meters in the air. Because that value 12 out the front, it's going to end up being our y-intercept. So just looking at that equation, we can start to grab that information. All right, so let's go through and finish off some of these questions. So question A, literally just substitute. It wants to know the height of the ball after the 5th bounce. So we're going to do 12 times 0.6 to the power of 5, which is 0.93312 meters. Doesn't ask us. It asks to the nearest centimeter. So remember, centimeters, I need to multiply that by 100. So multiplying it by 100, I move it 2 decimal spots. So I'm going to end up with 90, which is 93.3, which equals 93 centimeters. B says graph it. So quickly, just again, constructing a table of values. 12, 7.2, 4.3, 2.6, 1.6. Here you can see it's starting to decrease, but then its decreasing rate is slowing down how high it's getting off the ground. So it's getting closer and closer to the ground with each bounce. 1.6, 0.9, 0.6, 0.3, 0.2. So as it's going down, you can see we lose 5 meters initially, and then we're losing 3, and then we're losing 2, and then we're only losing 1, and then from the 5th bounce onwards, we're losing less than 30 centimeters and then 10 centimeters. So it's bouncing and slowly getting close to the ground. That's that decaying. It initially loses value quickly, but approaches the ground kind of slowly. So starting off, I know we're going to have, so that's 0, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bounces. It only says graph to 8, but that's all right. Now I need to go 2, 4, 6, 8. Yeah, 2, 4, 6, 8, 10, 12. So just points for reference. I know it's going to start at 12. After 2 bounces, I know I'm somewhere near 4 meters. After 5 bounces, I know I'm somewhere down near a meter. So just a rough guide for myself. And this needs to be a curve that drops down and then gets close to that x-axis, but never is going to actually touch it. So it's coming, let's start that again. It's coming down, curling around, getting close to that x-axis, but never touching it. And remember, don't forget to give it a name, and this was h is equal to 12 outside of, what was our equation again? 0.6 to the power of b. Alright, so that nice gentle curve that as you get closer and closer to the x-axis, it flattens out. That's our decay curve. A couple of points just to help give yourself a bit of a guide. Again, doesn't need to be extremely accurate. You can't get this pinpoint accurate as long as it's got that nice curve to it. Question C, we've already covered. It's 12 meters in the air, and we can read that from our y-intercept. Question D says, estimate after which bounce the ball will rise to 12 centimeters. Well, I know after 8 bounces, going back up here, at 8 bounces, after 8 bounces, we're 20 centimeters in the air, so I'm a fair few away still. By getting close, so let's just go 2 away from that, because seems right. I'm going to guess 10, and when we guess 10, when we sub 10 in, I get 0.0725, blah, 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 which is 7 centimeters, so that's too low. I know 8, so it's got to be somewhere around 9, because we know 8 is 20 centimeters, so I'm just going to throw in 9, and 9 is 0.1209, which is 12 centimeters. So that's very close. So we're going after the 9th bounce. So after the 9th bounce, it will reach So just to clarify here, that all the bounces before the 9th one, the ball does pass 12 centimeters in the air. Remember, we've initially dropped it from 12 meters, but what we're looking at here is I've dropped it and when it bounces back up to 12 centimeters. All right, that's as high as I want it to be. Question E, and I'll just scroll back up to it for a second. it says, what are the limitations of this exponential model for very large values of b? So the limitations. Well, we know that exponentials have an asymptote. That is, it's never going to equal 0 in this model here. All right. However, we know that dropping a ball and a bouncing ball at some stage, the ball will stop bouncing. We know the ball's going to stop bouncing. Science laws, gravity will stop it. So that kind of contradicts itself. Our model says you're never going to get 0, so it's always going to bounce and be some small height off the ground. The reality is, at some stage, the ball will stop bouncing. So that's the limitation of our model here, is that at some stage the ball will stop bouncing. So h equals, what was it? It was 12, 0.6 b is only valid for a limited number of bounces. Because at some stage that ball is going to stop bouncing. And the reason that we would go, well, it's okay to use this because this graph is the best description of what happens. And then we put that little asterisk and say, this is the best description that happens, but it's only good at describing this ball bouncing for, 20 bounces. The 21st bounce, the ball's actually sitting on the ground, but the math says it's still going to be some height in the air, but that's what we say. It's only good for a certain range because that's its best fit. So in summary, exponential growth and decay. Growth will occur when that value of a, our base value, is bigger than 1, and we've got a positive power of x. Exponential decay occurs when our power is negative, or when our power is positive, but that a value was a decimal, and we saw that in the example we just done with our exponential, with the ball bouncing. When we multiply our power, like 2 to the x, by something at the start, like we just did here with 12 times, that's going to be our y-intercept. And the initial value is going to be our y-intercept. It's going to be our starting position. So this ball we just dropped starts 12 meters in the air. And we just need to think about applying that to whatever kind of situation we're dealing with. All right, I hope that helps you guys.